All right, howdy everybody. It is time for your very first distance learning lesson. So here we are going to be reviewing topic 1.1. I should write that there, topic 1.1. So we are looking at the fundamentals and the particulate nature of matter at this moment in the mole concept topic. Now what I'm going to do is I'm going to explain 5 free response questions that are right here, and we will one by one, and you are expected to go through and complete the multiple choice quiz that is on in thinking. We will stick to that for the next couple of weeks, and then we'll probably change to something else. All right, so for number 1, it says to state the equation including the state symbol for the following reaction. So we want to add dilute hydrochloric acid to solid calcium carbonate to give aqueous calcium chloride, carbon dioxide, and water. So let's just go ahead and start writing that out. We have HCl, which is aqueous, and solid calcium carbonate. And it says it was solid, so there we go. Now it said that that was a dilute hydrochloric acid. So we should know that hydrochloric acid is HCl, and you should know that HCl is all acids are written with aqueous symbols. All right, and then we will make aqueous calcium chloride and carbon dioxide and water. Now we should know by now carbon dioxide is always going to be a gas unless it's otherwise specified as solid carbon dioxide. If since it says water right here, we will say it is a liquid. Okay, because water is a pure substance. Water is for sure a liquid. It is not aqueous. And so that's it, right? Well, unfortunately, we have to balance it, and we have Cl. We have our hydrogens are unbalanced, and our chlorines are unbalanced, so we need to put a 2 right here. We're all good to go. Now, you should remember that that is an acid-base reaction, right? We have HCl and calcium carbonate. That is going to make CO2 and water. That actually always makes H2CO3, carbonic acid, right here, but then it decomposes into CO2 and water. Okay, so a little bit of acid-base chemistry to help you review. So we should remember that from our acid-base unit, but hopefully you are getting that now. The idea is just to make sure you understand the state symbols and we understand the balancing. Now, for number 2, the reaction between ammonia gas. Now, you should know that ammonia is NH3. That's one that IB expects you to know. And it's a gas. And then oxygen gas. Well, you should know that oxygen is diatomic as well. Excuse me. And to give nitrogen oxide, which would be NO, and a gas, and water. Again, it said water, so we'll make it a liquid. So this is an NO. Well, nitrogen, the reason why I chose NO is because it said it was nitrogen 2. So that means that this is a positive 2, and you know that oxygen is a minus 2. If you crisscross those, you end up with N2O2, right? But actually, they cancel out, and in a covalent compound, it should be written as the lowest subscript. All right, so that is just NO gas. So let's go ahead and balance this bad boy. What we are going to do is our nitrogens are balanced, our hydrogens are not, and our oxygens actually are balanced right here. So we have a 3-2 combination. The magic number of the 3-2 is going to be 6. You ever know that if you have a 2 and a 3, it's always going to make it, you want to make it a 6. So I want to turn the 3 into a 6 by putting a 2 here. 2 times 3 is 6, and 3 times 2 is 6. That should help you balance things most of the time, but unfortunately we have 2 in, put a 2 here. Unfortunately, when we work it out, we end up with 2 oxygens and we end up with 3 oxygens. That's 5. No way we can make 5. We can make that 5 halves. I'm not sure that IB would accept that, so we should actually go ahead and probably cancel that out one more time. Let me get a red pen. And let's up that by 2. Okay. So that would be the best way to write that one. That's the one I would feel the most comfortable with. You could probably get away with 5 halves, but that is going to be the preferred way. All right, number 2. Now it says to state the ionic equation for the following reactions. Now I do not recall us actually going over this once, but I do go over it for my AP students. So when it's talking about the ionic equation, it's talking about the net Ionic equation, which means that we are going to remove all spectators. You may have come up with this when we went through our redox unit. I talked about spectator ions, which are the ones that don't really matter in the reaction. So we have to try to break this apart, this first one, and see if we can figure out which one is a spectator. Now, the way that we do that is we're going to take these and we're going to take barium, and that was a 2 plus. And then we have chlorine. I'm going to ignore state symbols right now because they're kind of annoying. And we have chlorines. Now there are 2 chlorine ions, so I'm putting a 2 chlorine ions right there. So that's how I take care of that Cl2. Now there are 2 silver ions. That's silver's 1 plus. And then there are 2 nitrate ions. We got that from there, 2 nitrates. And then there's 1 barium 2 plus, and there are 2 nitrates over here from this guy. And then there is 2 silvers, and let's see, 2 chlorines right here, excluding all the state symbols. So what I did is I just broke them all apart. Now, actually, what I shouldn't have done is I shouldn't have done this. I made a mistake because this guy right here is a solid. Now, what is going on right here is whenever these solutions are dropped into water and they're dissolved in water, the barium chloride is going to split up into Ba2 plus and then the Cl minus, and those ions are going to be swimming around just somewhere in the solution in a homogeneous mixture. Okay, so and these are swimming around homogeneously, and these are swimming around homogeneously, but this is a solid. It's not going to be homogeneous. Okay, with the mixture, it's going to be just its own substance. So it should be written as AgCl and just combined like this. So what we're going to do is we're going to cross out anything that is the same on both sides. So we have 2 nitrates here, we have 2 nitrates here, so we're going to cross those out. And then we're going to cross out the bariums right here. Now what actually mattered in the reaction was going to be the chlorines and the silvers, okay, to make AgCl. Now that was going to be 2 AgCl. So we're going to have 2. Normally the cation is named first, and then 2 Cl minuses, and there are 2 AgCl right here. Okay, and let's go ahead and put those state symbols back. All right, and now those 2's are unnecessary, so I can drop those, and so my final answer ends up just being the same without the coefficients. Okay, that was a lot of explanation for something that is actually quite simple to see. What you were going to look for is that precipitate and the one that is going to be changing. Here you notice that we start with 2 aqueous solutions. We're going to end up with another aqueous solution, so these are obviously spectators. Okay, the sodium and the chlorine are spectators. the things that aren't the sodium and chlorine, like the carbonate and the hydrogens, are going to be the ones that we care about. Okay, it's basically the ones that change phase. So let's take a look at that one. Our answer would be, if we just took that carbonate, well, when carbonate is a 2 minus charge, and then if we took 2 chlorines, oh, not 2 chlorines, come on, Mr. Russell, 2 hydrogens, and we made CO2, and we made water. Okay. Yep, so we have the same atoms, right? We have oxygens, carbons, hydrogens. We're all good. So we'll keep the gas, we'll keep the liquid, and we will have to keep that 2 there, okay, to make this equation balance, okay? And that's going to be aqueous. Hopefully that's all good, the way we are right there. Question number 3 says to outline how the following mixtures could be separated into their individual components. So first, how do we separate a saturated solution of sodium chloride? Well, so let's think about that. What kind of mixture is that going to be? Well, try to imagine it. Sodium chloride is going to look like a liquid. It's going to be the liquid phase, but it's going to be all the sodium chloride that's dissolved in water, right? Okay, so let's just draw a bunch of those little ions that are floating around homogeneously. The key here is that this is a homogeneous sample. Okay. Now, the way we would separate it is probably just going to be distillation. Now, when I describe distillation, I'm usually describing the apparatus or the organic apparatus that we would have, where we would be just where we would end up having a column right here. We'd have our sample down here at the bottom, and then we'd have a column, and then it would end up, coming over, let's see, into a cooling area and then collected off into here. Right? That is normally like that, but this is not actually, but that would be called a fractional distillation. Okay? The easiest way to take care of that one, this one, is to just heat it up, boil off the water, boil the water away, and NaCl is the solid left over. Easy. Okay? That would be the easiest way to do it, and that still qualifies as distillation. Now for number 2, it says to a mixture of hexane and octane. So we have hexane and octane. Now the trick here is that both of them have similar boiling points. Now you could actually look that up in your data booklet. So that the IB would expect you to know that, because those things are given to you in the data booklet. Since they have a similar boiling point, they also have the same London dispersion forces, similar. They also are similar compounds, because this is going to be 6 carbons, right? And this is going to be 8 carbons. They're very similar. So they're going to make a homogeneous sample again. Homogeneous. Now, because they have similar boiling points, we can't just use a simple distillation like we did up here, right? Both of them will boil off at the same time. So we have to use the fractional distillation. Some of them will boil off first. The lowest boiling point will boil first, and then the highest boiling point will remain in the solid, okay? So that would be the best way to separate hexane and octane. Now for number 3, an ink that contains two colored dyes. Now, you may remember this from our bonding unit. We did chromatography. If you remember, we had a piece of paper, and we ended up setting two inks right here. Let's say our blue ink, and we have our red ink, right? And if we use some methanol here, the methanol would travel up the paper, and let's say the blue ink traveled up to here, and then the red ink traveled up to here. That could be a separation between the two. Okay, I forgot to mention that this would also be blue and red, and this would also be blue and red. Okay, so we would, to make that make sense, we would end up with this. Okay, there, that makes sense. So if this was, both of these were blue and red, and so the blue ones would end up being on the bottom, and then the red ones would be on top. So the short answer for this is to use paper chromatography. All right, that's a good way to separate those mixtures. The diagram below shows a cooling curve for stearic acid. So we want to determine the melting point of stearic acid. So what this is, we have time plotted here. Sometimes you might actually see heat or heat added on the x-axis, and we have the temperature here. So as the temperature decreases, the temperature stops decreasing for a little bit, and then it decreases again. Now, this is normally given to you. I remember teaching this to my pre-AP students as this type of curve, right? This would be a heating curve since we're going up in this direction, but this would be a cooling curve since we're going the opposite direction. It means the same principle here. So the melting point is when it goes from a liquid. This implies that it's a liquid, and this would be a gas. So the phase change that is happening right here is going to be the liquid plus, gas, solid. Come on, Mr. Russell. This is going to be the solid. Okay, so we have this flat part right here, this little zone, is going to be your liquid plus your solid. So this is where the melting point is. It is at approximately 70 degrees. Okay, 70 degrees Celsius. So that's my answer for 70 degrees Celsius. Okay, now it says to explain why the temperature remains constant between B and C. Okay, so why does it? It's a good question. Now, to really explain that, let's think about this. So we have the solid, and we go to liquid. We go to a gas. Okay. Now, as we change phases from solid to liquid to gas, we are having to add heat, right? Makes sense. Okay. Just think about a block of ice. To melt a block of ice, we have to melt right here, and we have to add heat to it, right? So let's imagine that block of ice. Okay, this is ice. We are going to have to put heat into the ice. Now, if you know where I'm going with this, since we're putting heat into the ice, that means that melting anything going this way, in this direction, from a solid to a liquid, is going to be endothermic. Now, that actually makes sense because if you go from a liquid to a gas, it's also endothermic. That makes sense when when your sweat evaporates off your skin, it cools you off, right? That's because evaporation is going from a liquid to a gas. It's an endothermic reaction. That's why we sweat, okay? Now, a lot of students will screw that up big time because it feels backwards. So go ahead and just bang that into your head. Like, really try to write it down yourself and think solid, liquid, gas, and really think, okay, all right, going this way is endothermic. and going this way is exothermic. Students don't like to do that because they don't like to put exothermic near the coldest one, okay? And they don't like to put endothermic near the hottest one. But that is right, okay? So make sure you really think about that. Think about in terms of heat being added to the system. Okay, so I told you that to tell you this. Why the temperature remains constant right here is because as it decreases right here, this is actually going to be an endothermic reaction, okay? So we are, as it's going from a liquid, as a liquid to a solid, this flat part is when it's going to be exothermic, okay? It is actually going to be releasing heat while it's trying to cool, so it counterbalances it and ends up being at that flat point. That counterbalance between the exothermic and the exothermic reaction of the particles themselves and the decrease in heat is going to be create that flat part. Okay. Now, so the last one, question number 5, deals with atom economy. And this is actually very simple, but I'm not sure we really went over it too much. So atom economy is says that the metal tungsten, which is the symbol W, can be prepared by reducing powdered tungsten 6 oxide using hydrogen gas at 850 degrees Celsius. The equation for the reaction is listed here. Calculate the atom economy for this reaction. So what we are going to do is atom economy is the mass of our product, of our desired product, divided by the mass, total mass of products. Total mass of products. Times 100, because it's a percentage. Okay, so this is could be referred to as a percent atom economy. Now, basically, what that's saying is that when producing these, and if the goal is to produce tungsten, like it is in this example, and if it's being prepared, we are going to end up with some byproducts or some side products, aka byproducts, that's what we call them in America. And we want to produce the least amount of byproduct as possible. We want this. This is the one we want. So there are a number of things we could have started with that will give different products, right? So let's say that we started with W. I'm just going to make something up. What if we ended up with W 208 instead? Right? Well, that's going to have a different set of products, maybe a different coefficient of water, different coefficient here. So what we're going to do is, the point of this is that the reason why we would do that is so that we just want to understand the correct number of atoms. So what we're going to do is we're going to take the mass of our tungsten, and we're just going to look up the atomic mass of tungsten, which is going to be 183.84. That's just the molar mass of tungsten. And we're going to divide it by our 183.84. And then we're going to multiply 3 times 18, right? Because that's the molar mass of water, okay? So that's our total mass. Multiply by 100, and that is going to give you a total of 77.3%. Okay, so it's very simple. You are going to simply look for the one that is supposed to be produced, and then you are going to take that and divide it by the total, and you get your percent. All right, thank you.